Good evening, folks. In your last video, you looked at a pinned beam which was constrained in equilibrium by a cable, and it was basically a rigid body problem. The next sort of logical step in the progression would be to clip the cable and look to see what was going on with the acceleration of the center of mass of the beam, and also what was happening with the angular acceleration of the beam as it rotated about the pin. This is essentially a Newton's second law problem, just like the rigid body problem was, except the acceleration and angular accelerations aren't zero. This problem you're about to see is a little more complex. When I was taking classes in this stuff, it used to really irritate me when professors would give me really simple problems in class and then turn around and give me really hard problems on the test. I used to think it would make more sense to do it the other way around. So I'm giving you something that's got a little bit more meat to it, just because I think it'll be a little more educational for you and you'll be able to see some of the complexities. Anyway, enjoy. So here is our quote-unquote little bit more complex beam problem. It consists of a pulley which has welded to it an arm which has at its end a lump of material attached to it. When we release the system, it's going to angularly accelerate like so. So I've become enamored of animations, which you're about to see. I've included here the gravitational force acting at the center of mass of the arm. I've shown the gravitational force acting on the lump, which we're going to track as this thing rotates down. I haven't put in the forces at the pin because it doesn't have any effect on the actual acceleration of the system. And superimposing everything on top of everything else, there is the motion. So the question is, when the arm is at some arbitrary angle theta, as the system is angularly accelerating about the pin, what is the acceleration of the center of mass of the arm? Friendly warning. You may be tempted to think that because you're looking for an acceleration, that the key is to sum up the forces in the x direction and put it equal to ma sub x, sum up in the y direction, put it equal to ma sub y, and from those two equations figure out a sub x and a sub y, from which you can figure out the magnitude of a. That won't work. In those two equations you will have the two unknowns a sub x and a sub y. You will also have two unknowns wrapped up with the forces at the pin, h and v. Four unknowns, not enough equations to solve. A much more reasonable way to do this is to sum the torques about the pin, figure out what alpha is of the system about the pin, and then use the fact that the pin is a fixed point and the fact that you know that the acceleration of any point r units away from a fixed point is equal to r alpha. You know alpha, you can figure out r. From that you can figure out the acceleration of the center of mass. That's the way we're going to go about doing this problem. So here's our free body diagram, various forces due to gravitational effects, vertical and horizontal components acting at the pin, gravity acting on the pulley. These forces are not going to end up having any effect on the torque in the system. I'm including them here just to be complete. In later free body diagrams I probably won't even put them in. You might very well look at this and go, what the hell? There's no force to counteract h. In fact, if you think about the acceleration of the center of mass, it has a component in the horizontal, and that has to be matched up with some kind of force that's generating it. Where that force is coming from is the pin. The pin is executing a force in the horizontal, which is allowing that acceleration to happen in the horizontal as this thing rotates around. So we're going to sum up the torques about the pin. As I said earlier, H, V, and mg are going to generate no torque about the pin. As you know, we have three different ways of doing a torque calculation. I'm going to use the R perpendicular approach, or the moment arm approach. To do that, I need to know what the shortest distance is from the point about which I'm taking the torque to the line of the force that I'm interested in. That shortest distance is this distance right here. This distance is r plus L over 2. This angle's theta. This is the adjacent side to that right triangle. which means r perpendicular is r plus L over 2, all quantity times cosine of theta. So doing out the math, the torque due to the gravitational force acting on the arm is going to be the magnitude of that force, which is mg, times its r perpendicular, which we just calculated. That's going to be a negative torque because it's tending to make the body want to rotate clockwise. The torque due to the gravitational force on the lump is going to look similar. It's going to be mg times its r perpendicular, which is going to be r plus L, times the cosine of the angle to give us this distance. That's also going to be a negative torque, and that left side is going to end up equaling the rotational inertia net about the pin, moment of inertia, times the angular acceleration about the pin. And that's also going to be negative because the angular acceleration is clockwise. So part of what's tricky about this problem is figuring out what I about the pin is. And the reason why it's tricky is that there are three contributors to that moment of inertia. There is the pulley, there is the arm, and there's the lump at the end. So the net moment of inertia will be just the sum of the moment of inertias due to those three contributors. Probably the easiest to figure out is the moment of inertia of the lump, because it's essentially just a point mass rotating that many units, however far that is out, from a fixed point. The one moment of inertia relationship I've asked you to memorize is for a point mass, and that's just mr squared, where the r term is just the distance between the axis and where the mass is located. In this case, that's just r plus L, so the moment of inertia of the lump about the pin is just going to be m sub L times r plus L quantity squared. We can take the pulley as being approximated as a disk, and the moment of inertia for a disk is a half mr squared. And the only thing that's really tricky is figuring out the moment of inertia about the pin of the arm. So we know what the moment of inertia of the arm is about its center of mass. It's 1/12 ml squared. So we have to use the parallel axis theorem to figure out what the moment of inertia of the arm is, not about its center of mass, but about the pin. And that relationship essentially says that if you want to know what that moment of inertia is, you take the moment of inertia as it stands about the center of mass, and you add to it a fudge factor. And the fudge factor is equal to the mass of the structure, the mass of the arm in this case, times the distance between the two axes, quantity squared. That distance in this case is L over 2 plus R, which is what we have right here, quantity squared. Under normal circumstances, you would know something about R and L. You'd probably be able to simplify this, maybe combine these two so that you'd have maybe a fraction times m times L squared. Can't do that in this case because we just don't know how L and R are related, and so we're just going to have to deal with the mess. So with all that information, here is the sum of the torques. Notice that I've put in the signs. The torque due to mg is going to end up being negative in both cases. The angular acceleration is negative, so I've got negatives all the way across. Notice on this line I've multiplied everything by -1 to get rid of the negatives. I about the pin is going to be the sum of I due to the lump plus I due to the pulley plus I due to the arm, and here are all those terms. So we just do math, 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 and by the time we get done, we have an expression for alpha. If you remember, though, what we were trying to figure out was the acceleration of the center of mass, which essentially is the acceleration of a point on the arm, basically halfway up the distance of the arm. We know what the angular acceleration is about the pin. We know the distance from the fixed point, which is the pin, out to that point of interest. It's just capital R times L plus L over 2. And if we multiply that distance out times the angular acceleration, it will give you the acceleration of that point. And so that's basically what I've done here. This is little r times alpha, giving you A of that point. And that's the solution to our problem. So just to sort of add the icing on the cake, as this thing is rotating down, when it's in this position right here, you'll notice that the torques, due to these forces, the forces are going to be passing through the pin, which means the torques are going to end up being zero, which means you would expect that the angular acceleration would be zero. And if you pull those cosine functions out and just stick the cosine over here in the angular acceleration function, and you put in 90 degrees or minus 90 degrees, lo and behold, you get a zero, which is exactly what you would expect. Anyway, that's it.